supporting building owners and institutional leaders in achieving their climate and energy goals. Craig Altomos is the Director of Strategic Partnerships at GreenerU. Craig has 20 years of experience in climate and energy policy in both the civic and private sectors. He's also a licensed attorney in the Commonwealth of Massachusetts. Thank you so much to the both of you for being here, and I'm excited to hear how your presentation goes and how the conversation goes afterwards. So thanks a lot. Pass it over to y'all.
Awesome. Thanks so much, Paul and Amy. And Matt, thanks for having us here. I will pull my screen up here. All right. And how's that looking? Good. All right. So as Paul mentioned, I'm Rob Durning. I'm the CEO of GreenerU, and we have been in business now for 17 years and helping our customers plan for, engineer, and construct their energy and climate goals over that time. And on here on the cover slide here is a photo from a recent geothermal conversion we did this was our pilot well, which became the first production well. And we did this the day after Christmas, which I think was the most excited anyone's been to be at work the day after Christmas. But we had this nice little holiday themed photo that we took here. But just to give you a bit more of flavor on GreenerU, who we are, we really try to help owners, especially community-based institutions, understand what their goals are around climate and decarbonization of their existing buildings, and then take that design build route where we're helping them actually advance those projects, those goals into fundable projects. And those projects can run the gamut from the low-hanging fruit, from lighting that's still out there, envelope improvements, targeted window replacements, all the way through the stickier problems like electrifying their heating, finding opportunities for heat recovery, and sort of going fossil fuel free. Across our 17 years, you'll see in our name we have the giant U at the end. We started out working with colleges and universities who were some of the first institutions to really match that blend of carbon reduction and sustainability goals with their energy work. And over our history, that mandate to decarbonize our existing buildings has only expanded. And so for institutions who have that long-term view that they're going to be in their buildings for the next 25, 50, 100 years, our approach seems to match really well, where we can help them establish what those goals are, find the right projects that will meet those, that match their goals, and then help them get those done. And so that has expanded to include museums, other nonprofits, houses of worship. And more recently, what we have come to find is we're increasingly finding customers with a plethora of options in front of them to electrify their heating and cooling. They could go air source heat pump. They could go air to water heat pump. They could go VRF. They could go geothermal. And it comes with a lot of tricky decision making and sort of understanding, sort of peeling back the layers of the onion to understand, what are your long-term goals and how would one decision today impact the next 20, 30, 50, even 75 years for a well field, and then sort of making, coming to a consensus on what those decisions should be. And so, the value that geothermal provides is something we want to get into today. And what we have found is, there's a fair number of myths out there around, what geothermal is and what it isn't, and how to think through those types of problems. So this is, the problem that we're facing today is primarily an existing building problem. I think by and large, design teams out there have come to find a economically feasible way to design new buildings that can be net zero or even positive energy, between really tight envelopes and, sort of a green space where you've got a lot of site work already going on. Maybe it just makes perfect sense to drop geothermal wells underneath the foundation of a building. that might already be going up. But 80% of the buildings that we know will exist in 2050 have already been built today, and so this isn't a problem that we can sort of new construct our way out of. We need to figure out a way to decarbonize and go fossil free in these existing buildings, especially when you're dealing with maybe historic preservation, or other buildings that programming will be in for the foreseeable future. And so many of these are already standing. Most of them are already relying on fossil fuels. That for some of the oldest buildings that we're looking at, we're putting the geothermal pumps in what used to be the old coal room, and then it became the oil storage room, and that then they connected gas to it 25 years ago, and now there's those boilers are starting to fail, and they've got to figure out what to do. And so they've been locked in this sort of continual fossil fuel upgrade cycle, and they're at a point now where they don't know which way to turn. Right? We know we're not going to go. We don't want to go fossil fuel. But what sort of solutions are in front of us? So, you may be in a building that's facing one or maybe even all five of these potential variables, right? We just said end of life systems. The status quo for the last 100 years is you call your mechanical contractor when your boiler is about to fail. They give you the most efficient option, right? Maybe it was 80% efficient oil fired back in the 80s and 90s, and then in the 2000s you converted to natural gas, and then maybe later on you could go to a condensing boiler, and so you got up to maybe 96% efficient. But now you're looking at a number of heat pump options with people talking about efficiency numbers in the 2, 3, 400% range, right? How do you make that decision? But you also don't want to, if we're going to be electrifying, we're also going to be making a commitment that our utility bills may be either increasing if we've got a really good gas rate now, or we're sort of trying to balance what our long-term operational costs are going to be. And so understanding the implications of that long-term operating cost for the next 30 years when you make that decision today is really important. And if you can, maybe pay a little bit extra on the front end to help lock in longer equipment life or lower operating costs moving forward, you can sort of justify that premium upfront. We're also talking with a lot of customers who are dealing with comfort, resilience, and maintenance issues, right? That there may be areas that aren't currently cooled that they want to expand cooling to, or they have an area that's particularly humid or not well controlled on temperature control because it has a leaky historic envelope, and so addressing some of those things up front to help right size the heating and cooling system long term. Others may be in, if you're in Boston or Cambridge and even the state of Massachusetts has started their large building energy reporting programs, you may be facing regulatory requirements that will require you over time to reduce the carbon intensity of those buildings. The first year of compliance payments kicked in here in 2026. The way they design the program, most people are finding that they're below the thresholds for this 5-year cycle, but are facing a cliff come 2030 where they're going to need to figure something out here. And then also, just in meeting your institution's own mission or stewardship goals, you may have made more aggressive commitments than a building performance standard has put in for, say, 2050. You may be looking at 2030 to be carbon neutral and 2040 to be fossil fuel free. And so figuring out those decisions, those are sort of long-term horizons, but decisions you make today may sort of, lock you in past those deadlines. So we talk a little bit about how geothermal works. So, what we'll get into a little bit as we get into the myths that we're finding later in this presentation. What geothermal is a series of boreholes that create an underground battery for I think an interesting analogy where you're looking to pump medium through that battery that pulls heat out of the ground in the winter and exchanges it through a heat pump compressor to heat your building in the winter. And then in the summer, you're taking that same principle in reverse, and you're pulling the heat out of your building and you're pumping it back into your battery. You're refilling that heat into the earth through these boreholes throughout the summer, and storing it for the winter months. And the beauty of the ground is that beyond the frost line at 4 feet or so here in New England, the earth is a very stable temperature. And so it acts as a great medium to store energy. And we can reliably know that the temperature of the medium coming out of the earth is going to range somewhere between 45 degrees and sort of the coldest of winter, and 55 to even 60 degrees sort of as you get towards the end of summer and transition into that heating season. And so heat pump equipment manufacturers can design a piece of equipment that works very efficiently within that very tight range of temperatures, versus say an air source heat pump or air to water heat pump, where the medium that you're looking to transfer heat to or from, depending on your heating or cooling season, is going to swing wildly from possibly 0 degrees, that's the design temperature here in Massachusetts, up to say 95 degrees in the summer. And designing a piece of heat pump equipment that can operate at that 200 to 300% efficiency is going to get more difficult to do as you reach the extremes of the temperature that you're trying to exchange that heating and cooling with. So here in heating mode, you're going to have your wells, and you see if I can pull up a pointer here. You're going to use your pumps to pump a medium through your wells here. You're going to put it through a heat pump, and then you're going to distribute that hot water, which could be somewhere between 110 degrees and 130 degrees, up to air handling units, where you might put it through a coil and deliver hot, warm air to the building, or you might be putting it out through baseboard radiators. And what we illustrate both scenarios here, because in a recent conversion that we did for a church in Wellesley, Massachusetts, we were able to reuse a lot of the existing infrastructure here in the building. We were able to reuse the coils in the VAVs and the baseboard radiators around the building, even though they were originally designed to handle 180 or high temp hot water that would have come from your boiler system. And instead, we added air handling units up on the roof and connected to existing ducts to basically carry more of the heating load up here, because it was less disruptive to all the spaces down here. And so we were able to do this retrofit while maintaining occupancy through the building, sort of keep most of the construction up here, down here in the basement where we were out of sight, out of mind, and then up here on the roof. Obviously the drilling was impactful from a site perspective, but the building, as long as we could maintain sort of safe ingress and egress to the building, we were able to do that in an occupied building. And then here in the cooling mode, one of the benefits is that with these wells, given how intensive, how much more heating load we usually have here in New England, we're actually going to bypass these heat pumps in the summer. We're going to try to take the mechanical cooling out of this building and just pass this water right across these air handling unit coils, and use that 45-degree water that we cooled, essentially cooled the ground as we tried to extract heat out of it all winter. We got those wells down to say 45 degrees, and now throughout the summer we're going to pull that water out of here, and as much as possible we're just going to try to use that water directly at this air handling unit. So their cooling load is actually going to possibly decrease their annual electric rates. We're just entering our first cooling season here, and we'll have more data on that as we get across. But and as these wells heat up, then if we need to, we will continue. We will introduce the mechanical cooling through the heat pumps to deliver the cooling to these buildings. So, somewhat technical. Explanation of sort of how a heat pump works in general, and how geothermal works, and why we're sort of making that upfront investment to sink the boreholes into the ground. But as we talk to more and more customers about this geothermal, we've come across a lot of misconceptions in the industry. I wouldn't say misinformation, but just myths that people don't quite understand, what we're really talking about here. So I want to just briefly run through sort of some of those myths to hopefully clear those up and get people thinking in the right way about what this is. So first myth, geothermal is too expensive. We've seen a lot of feasibility studies where geothermal ends up getting put right at the bottom of the page as sort of and we also considered this, but you're not going to want to think about that because it's too expensive. Number two, the ground around here isn't warm enough. Number three, you need a lot of open land to be able to do this. Number four, you have to rip out your whole system. I just sort of explained in the last example, an example of how we were able to do that without ripping out the entire system. And number five, the incentives went away. A lot of misconceptions around commercial investment tax credits around geothermal systems. So looking at the myth of geothermal is too expensive. On a first cost basis, that first investment that you will make into a heating and cooling system, geothermal is more expensive. It is, on the order of, what we are finding is somewhere between 70 and 100% more expensive than, say, an air source heat pump option. However, what these numbers usually don't take into account are your either state or utility incentives and your federal tax credits, which we'll get into a little bit later, and how those still exist. But when you start to take those into account, you can actually bring the first cost of geothermal, that initial net project cost of investment, down into at least somewhat of a parity with an air source option. And that's what we're finding, with our subcontractor pricing, and when we do the pro forma for our customers on what this is going to cost. But what we want to really drive home with our owners is that even a higher first cost may create a better long-term outcome. And as I started to talk about earlier, when you talk about energy costs over time or how long that asset is going to live versus, say, an air source option, what your operations and maintenance might look like for a centralized geothermal system versus a distributed air source system, and your sort of comfort and resilience long term, that's where you can really start to tip the scales. In general, energy costs over time, an air source heat pump project is generally going to run around 200% efficient, which means for every kWh of input into that heat pump, it's going to create double the amount of heat output. For a geothermal system, but as I mentioned, sort of it's having to create that heat, whether it's 0 degrees outside or whether it's 50 degrees outside, and it can't do that as efficiently the lower those outside air temperatures go. For a geothermal system, where you're talking about a very stable medium year round, you can actually run that system closer to 400% efficiency, and those are real world efficiencies that we're seeing here. So you're basically, if you're going to completely electrify and you're afraid of that sticker shock on your first electric bill, a geothermal is going to help alleviate that by creating, almost twice as much energy savings long term. The other big one to consider is capital replacement cycles. In a recent example, we considered the less expensive air source option was just 1-for-1 replacement of rooftop units that were, they had cooling on them and they were gas fired, and we said, well, we're going to go to a heat pump version. Well, an air source heat pump RTU is a great option, but it's going to have a shorter life. Generally, we're seeing those start to see increased maintenance and failure right around 15 years or so. The ones that are getting closer to 20 years are sort of, and really end of life. Especially here in New England, they're going to those compressors on those cooling systems, heat pumps, are going to be exposed to the elements year round. New England winters, you're not going to get the same life out of those versus, say, what we ended up going with instead was that all of the compressors and heat pump equipments are down in the basement, so they're protected from the elements. They're going to have a longer life. And then up on the roof, instead of doing rooftop units with more moving parts, 7 fans, 7 sets of filters and belts and things to work through every time, we simplified the ductwork to go to 2 air handling units, and they're basically marine grade air handling systems. Now we have 2 fans, 2 sets of belts, a set of filters, right? We've simplified the mechanical equipment up at the rooftop level. We think that, between the heat pumps in the basement and the air handlers up there, you're probably going to be looking at, 25 to 30 years of life on those. Plus, your well field is a completely closed loop, underground, seismically safe type system. Ground loops are going to last 50 to 75 plus years. So, consider the total cost of ownership. And what we try to help our customers look at is, you may pay more upfront for the geothermal system, but when you start to factor in those utility costs and replacement costs and use sort of a life cycle cost analysis that your design teams might be looking at, you can actually get that ground coupled water source heat pump project to be, below the cost of the air source system all the time. In this example here, you'll see, sort of it's a bimodal distribution. We do these probabilistically so that, people are sort of can understand that there's uncertainty in trying to forecast out 25 years. In this scenario here, we were modeling what if we got the investment tax credit and what if we didn't get the investment tax credit. Since the bill was passed in July of 2025, that's, that uncertainty has since gone away. And what if we were to run this today, this sort of bimodal distribution would move entirely over to here, because this customer is on track to receive that investment tax credit. Myth number 2 is geography. The ground isn't warm enough around here is the second thing we've heard. And a lot of this misconception comes from an understanding of what they're doing with geothermal out west, which is actually, tapping into the magmatic zone of the earth where we can get really hot temperatures and drive that through a turbine to create electricity. We are not doing that type of geothermal. So in that way, the word geothermal can be a bit confusing, a bit misleading. What we're talking about is a ground coupled water source heat pump, where all we're really trying to do is find that stable medium to exchange heat from year round. And here, 31% of heat pumps are here in the Northeast, and they're working well. And particularly as systems have evolved and we've gone to closed loop geothermal systems. And here, myth number 3 here is the site, that I need a lot of land to be able to do this. This was the Wellesley Village Congregational Church. We just wrapped this project up last year. They made it through their first heating season, and it was a nasty heating season here. We had a lot of really cold days and some big storms that they had to contend with. As you can see here, this is a pretty tight site. We've got 3 major streets on 3 ends. These guys are right in the middle of Wellesley Center. And then the 4th side is a cemetery. And so, we really were constrained to keeping our wells in this very tight parking lot driveway area around the church. And we were able to do that. You can see here with this overlay, Central Street, Washington Street, Church Street. We were able to get these wells sort of around this site. We were able to get 18 wells into the ground here. Myth number 4 is about disruption, right? And how can we minimize the disruption to an institution as they're trying to consider their non-fossil fuel options. Converting to a boiler, that's a very easy disruption question, right? The mechanical contractor is going to wheel in a new boiler. He's going to hook it up. He's going to go through utility hallways and cargo elevators, and he'll be out of sight, out of mind in a boiler room. Simple conversion. All your existing terminal equipment in the space stays the same. When you're considering a heat pump, you're going to be working with higher efficiency equipment but usually that comes at a lower temperature. And so to be able to reuse some of your existing equipment, you need to be able to do that those load calculations to really understand how you're going to continue to satisfy the heating and cooling loads of your room. But there are some creative ways to do it. Anybody who tells you that it's completely out of the question without really studying it and seeing what might be possible, is probably, not looking at, trying to be creative in their solutions. And as a, climate forward company, we try to work with our customers to understand what is and isn't possible. And I've added here but it depends, because we also deal with some customers who say, I know I need to take this on. I know I need to get rid of my existing equipment. I've got 1960s fan coil units that are rattling in this space that distract from the programming that's going on in here. We need to replace that. And so, it's really about taking a nuanced look at what your options are and consider what those are. And the bottom line is, find a partner who listens, who's going to, take the time to study the options, help you understand what those choices are, the trade-offs that you'll be considering in making those decisions, and have honest conversations with you. And myth number 5, this is my last slide before I hand it over to Craig, but incentives. So, when it comes to climate-related initiatives, the bill that was passed in 2025 did end investment tax credits for solar and for residential geothermal, but it did continue commercial tax credits for geothermal through 2032. So anybody who's considering potential boiler replacement in the next 6 years, this is still going to exist. You need to start construction before 2032 to be able to apply for that. But it is still available. It is still out there. And the two big three big points around those tax credits to consider is there's a 30% base tax credit for geothermal. There are some stipulations for how you comply with that, depending on the size of the system, but it does sort of exist as a base incentive. And then there are adders, depending on the type of equipment you use. If you can source entirely U.S. made heat pump manufactured equipment and steel, you can get the 10% direct domestic content adder. And then for certain institutions within environmental justice and energy geographic regions, there's some additional adders there as well. And I'll just point out, for museums, many of which are operating as nonprofits, if you don't have a tax liability, you are still eligible for the investment tax credits through the IRA's direct pay program. And then the direct pay program was maintained through the bill that was passed in 2025. So with that, that's a very quick and brief overview of sort of, geothermal in its at its basis, and sort of some of the myths that we're hearing out in the industry. And hopefully some of this resonated with you. And with that, I will pass off to Craig, who will present on one of our partners.
Yeah, so just do a quick walkthrough of the Wellesley Village Church here, and then we'll also touch on the tax credit again, just to underscore some of those points at the end here. So next slide, Rob. So as Rob noted, the initial outlay for a geothermal system is a lot higher when you look at that first upfront cost. But once again, it kind of goes further higher when you build in contingency and interest you need to carry to pay for at least the tax credit component. But once you fold in the rebates and the incentives, again, you're looking at a pretty good price parity between the two systems. This is not true in every case, but this oftentimes can be the case. But the next slide, where it gets really exciting is as Rob said, looking at not just the capital cost, but looking at the utility spend, the replacement cost. the maintenance costs over the life cycle of the equipment. And so you look at this chart here, we're looking at the first 20 years, it's the darkest bars. And then as they get lighter, you're looking at the 35 and 50-year timeline. And again, for a museum that plans to be in that same building generally for the next 50 years, it makes sense to have that long-term perspective of not just what is this going to cost us today, but how is this going to allow our institution to sustain its operations over the next 50 years. And so again, the capital costs are about the same. The utility costs are lower over the first 20 years, and they get even lower over the first 35 and even lower yet over the first 50 years of this system. And again, these systems are expected to last at least 50 years for the wells, and probably a lot longer. But again, we haven't really gotten too many systems past 50 years yet. So exactly how long they last is to be determined. And then again, when you look at the replacement costs, you're looking at multiple cycles of replacing a gas system replacement versus the geothermal. Maybe in 50 years you'll have to replace the wells, and again, some of that mechanical equipment is going to have to be replaced in the short term. But again, the wells really should last that full period. So when you aggregate all these things together, you'll see that the blue bar is a lot lower than the brown bar. And so the geothermal again saves millions of dollars over that 50-year life cycle cost of owning the two different systems. So again, can be really financially attractive when you take that long term. So it's really a slam dunk. You take the long-term perspective. Particularly, next slide, when you don't just think about the financials of this, but then the co-benefits, right? Principally, the climate benefits. If we really care about climate change and want to do right by the world, make sure that there's a society to continue enjoying the museum that you operate. For this church, their current HVAC system, either way, we're going to see a pretty significant reduction in their emissions profile, whether we switch to an air source and heat pump, and natural gas hybrid system, or went all the way to geothermal. But again, the geothermal has a lower emissions profile, and then critically, because it is fully electric. If you either generate on-site solar to cover that electricity usage and/or purchase green electricity, you can basically get that system down to a net zero climate impact. And furthermore, again, this being in Massachusetts, which has a renewable portfolio standard that's increasing how much electricity is green every year, even if you do nothing within that 50-year time frame, I fully expect the New England grid to be completely devoid of fossil fuels within 50 years, right? And so if you do nothing else, you're looking to have no emissions by the end of the life cycle of this equipment. Versus if you have a new gas system involved, it's obviously not going to be a zero emissions gas system. You're going to be burning natural gas on site. And then, we don't really have a slide on this, but there's also the public health benefits of this, right? Where, when you have a gas system, you're burning fossil fuels, you're burning a lot of different chemicals that went into the fracking to get that fuel out of the ground. Those pollutants are going into the air right above your building and then filtering around into the community. And also some of that maybe doesn't get filtered out very well, and it stays in the building, and your visitors, your staff are breathing in those pollutions. So again, there's other benefits here besides the financials. Financially, the best decision. We don't even account for the cost to society into your staff and your members and so on. Next slide. So a little bit, Rob touched the tax credits pretty well, but just want to really underline this because I think that this is really key to making it work. So these remain fully intact through 2032. I'm going to just keep advancing here, Rob, as I go. So again, as Rob said, there's a base of 30%, and then if you use domestic content in that goes up to a 40% tax credit. And there's kind of two key components to that. One is U.S. manufactured steel or iron to the equipment, and then a minimum percentage of U.S. made components for the equipment. And then you can get an additional 10% adder for if you're an energy community, and there's a couple different criteria for that. I'm going to keep going. Yeah. So if it's an area that used to have a lot of fossil fuel employment, probably not as relevant for us here in the Northeast. But if you think of an area where there's a lot of coal mining or fracking or oil drilling, you can get extra if you do that. If it's a brownfield site is another example, which we do have more of here in New England. And then also just regions that have a really high fossil fuel dependency. And I'm honestly not sure how often that occurs here. I haven't looked into the criteria for that, but that's another area you might consider. And if you qualify for any of those, again, that could get you up to half of the system costs returned to you. Some other important things to note, again, as Rob mentioned, so there's this direct pay provision. So before the Inflation Reduction Act was passed, If you were a nonprofit, you basically had to like trade your credits with a private entity that would purchase them for you. Now that whole thing is eliminated, so you get 100% of the tax credit just sent to you as cash as a nonprofit institution. Also true for local governments. Um, and then what parts of the equipment are included? So we're talking about the heat pumps. You can just keep going on these. The ground loop, the bore field drilling, piping and distribution, the control and electrical. So if you have an electrical service upgrade, that'd be part of that. And then also the design and engineering work to bring the project to life. And so it does continue beyond 2032, but it starts phasing out. So in 2033, it gets down to 26%. In 2034, it's down to 22%. And then by 2035, it zeroes out. So it phases out pretty quickly there. So again, I think if you want to capture the full benefit, definitely aim for beginning construction by or before 2032. But again, there's still some benefits after that. And it's theoretically possible, if you just installed new gas boilers last year. Like I'm hopeful that a future administration, a future Congress may decide to extend these tax credits further into the future, but there's certainly no guarantee of that. So it's possible for you, but again, if you are thinking about replacing your HVAC system in the next decade, I would personally really think seriously about trying to do it in time to capture these very substantial benefits. And then again, different states have different levels of incentives beyond that. If you're in Massachusetts, if you're in Connecticut, those are pretty good. If you're in New Hampshire, maybe less substantial, depending on again kind of the state policy there. Um, but just to close things out and to move on to questions. So the bottom line here, geothermal is not right for every institution. It's not right for every building, to be clear, but you don't want to rule it out for the wrong reasons. I think, Rob, you want to keep going on these? Yeah. So again, I think the key part is to start with the building, not the technology. So we've had some customers come before us and say, yeah, we want to do geothermal. And we actually, as much as we love geothermal, we think that that's the wrong approach. It really should be, this is the building we want to decarbonize, and let's take a thoughtful analysis as to what the right approach is for this building, which may well be geothermal. But we think it's important to consider all the different variables. And so you want to, establish shared goals for the building. Maybe one of those goals is decarbonization, maybe getting oil and gas systems out. But again, for some buildings, the best way to decarbonize may be air source heat pumps instead of ground source heat pumps, depending on a variety of factors related to the building. You may also have a goal of adding cooling to the building if you don't have that yet, which again, both air source and ground source heat pumps can provide cooling as another goal. Again, cost savings may be the goal. You really need to figure out which is going to be the most financially practical one for you to achieve. So really thinking about what are the goals, and study all of the realistic options that could get you there. Make a fair comparison across those. And when we say fair, again, that's really where you're taking the full life cycle cost. So don't just compare those upfront costs, but compare also the incentives, the savings on operations, the savings on maintenance, so you can make a fully informed decision as you're weighing these different options. So again, not always the answer for every institution, for every project at every moment, but it's a really attractive one for some that hope folks consider as you move forward with your decarbonization goals. So with that, I think we'd be delighted to turn it over to some questions and or any comments or from the audience.
Should I just jump in, ask a
Please.
question?
Yeah, please.
So I'm with Paul. I'm at the Discovery Museum and also with Neil's former museum. So we're talking about doing a renovation addition to a building next year. And I guess the question would be, we know that the current heating system is failing. It's oil, unlike the rest of the new museum, which is all on the grid on our solar panels. I guess I'm trying to understand, like when you showed the map of the church, you said 18 wells. How do you decide how many wells would have to be drilled in? And you said those are all under their parking lot. Is that how that fit in there?
Yeah, so it's certainly, there are some rules of thumb out there, but it's very site specific.
Okay.
So, in the case of the village church, we went down 850 feet. We were able to hit competent bedrock very quickly. and we didn't have a lot of water in the wells as we were drilling them. So if we had encountered a lot of water as we drilled down, we may have capped those wells a little bit shorter and done more wells. We were also able to sort of create a more linear well design. The traditional well layout is a grid, but in a heating dominated environment like New England, those internal grid, the well or the bores in the center of that grid are going to have a hard time dispersing their heat outward because they're talking to the wells in front and behind and to the left and to the right of it, right? So you're gonna get better heat dispersion, better heat transfer on a well system that has less talking between those wells.
Okay.
Anyway, a very long way of saying it's very site dependent, and it's very sort of dependent on how you can lay out the wells in a way that maximizes heat transfer for the least amount of well drilling.
So in the process of, say, trying to being responsible and evaluating like what works best for this building, would you do test bores? I mean, because you wouldn't really know how far you'd have to go. I don't know. I guess I'm asking how specific or how significant is that, whatever the conditions are to the cost. Is that going to make a big difference?
Typically, our approach would be start with a feasibility that compares, say, an air source base scope with an alternative that is a geothermal. And if the economics make sense at a feasibility level, then we would recommend a test well to really dial in those thermal conductivity numbers.
Great. Thank you.
Insight and geological constraints, right?
But thank you for saying that we should think about the building first instead of like, oh, let's do geothermal, because I think we've got both sides on our building committee. People just say, oh no, we're going to do geothermal, and who cares what it costs? Versus like, does that really make sense for us? Given, I mean, we obviously have the climate goals in high priority, but right. So
yeah, and the economics completely change if you're talking about a new construction type project, especially if you're building towards the stretch code or the specialized stretch code where your envelope's getting much tighter. The incremental benefit of air source on a really tight envelope or on geothermal on a really tight envelope is going to be less than when you're trying to heat and cool a 150-year-old building,
right?
With that is going to struggle in that 0-degree weather in winter.
Yeah, Neil.
So I have a quick question. Ellen mentioned I used to run the Discovery Museum. 15 or 10 years ago, we looked into doing geothermal when we were doing a construction project. And frankly, the problem we ran into was the lack of knowledge and familiarity and ability to do analysis on the part of the HVAC engineers, the building architects, whatever. Has that knowledge base expanded, or is that why folks like yourselves are in business to sort of be that bridge between the analysis that's needed and the engineers that are out there?
I'd certainly like to think that we act as that bridge, especially where engineers may have a certain technology that they know that they're best at, and they'll sort of go down, want to push a project down a certain path, and we try to take a step back and be more on the aligned with the owner and say, well, let's not assume we know what the right answer is yet. But I will say that as closed loop geothermal systems have improved over the last decade, and as the IRA incentivized geothermal systems, I would say that the accessibility for owners to consider a geothermal option has increased, and therefore design teams have built out better capabilities to evaluate that.
So, somewhat related question that might help Ellen. At what point in a building design process would you be most helpful in getting involved in order for an owner to make a good decision?
Um, we have been involved across the gamut. I mean, even up through we're just talking to an owner right now that said, "I'm starting demo on my existing buildings in June. Can you drill a test well in July?" Because they want to think, in the 11th hour, somebody said, "Did anyone look at geothermal for this project?" And no one had. But I certainly think, that those decisions become more difficult the deeper into design you go, and sort of the changes that your design team may come back and say, well, that's, we're going to do this, we got to redo this. But I think from a, from an owner's perspective, where if you have one champion who's saying, I just don't want to rule out geothermal yet, really just continue to push the design team to consider those options, because on a new construction, I mean, they should be able to give those numbers to you, and then maybe bring in a GreenerU to help you look at like life cycle cost analysis and total cost of ownership, and do that energy model for you that says, here's what you're looking at over the next 30 to 50 years at a schematic level, and or even at a feasibility level, and then move on from there.
But I'll say too, yeah, I mean, Rob gave the example of the very late stage, but I think with this church, yeah, I know that we were in dialogue for at least a year right before. I think like really helping, like a congregation has a lot of decision making to go through. They had a lot of committees, and they had to have a congregation wide vote. And so we were brought in fairly early to help them as they were, going through that discernment process, to help educate the congregation about the different options, about the technology, and again, help them make an informed decision. So I think we're happy to get involved very early to help, again, do that education of folks, and to do some hand holding for folks who, appropriately, not everyone's an expert in HVAC technology, right? Like we all have different areas of expertise, and for most folks, that's not building energy systems. So helping people just to understand that, who are key stakeholders within an organization, or again, yeah, we can be brought in somewhere in the middle, or in some cases, yeah, fairly late in the game, but hopefully not too often.
Yeah, and maybe I'll just point out sort of a clarifying point. I see two different tracks most of our customers are going on. It's I have this new construction building, right? And so the first call is the architect. And so it's an architect led renovation or new construction type project, versus say an existing building it's coming more from an O&M type perspective, right? I know my boiler only has 2 seasons left. It's I don't have this in my capital plan for a renovation, but I need to heat and cool my building for the next, 10 years until that next renovation cycle, right? So you're sort of stuck in that in between that says, I need to do this, and here was how I would have done it 5 or 10 years ago. And now I'm faced with sort of having to weigh multiple options. So, there's two different ways of sort of two different tracks of thinking about those.
That actually triggers a curiosity for me. I don't work at any one museum. As a museum consultant, I see a lot of different kinds of buildings, and um, so like the Discovery Center that's looking at a new construction project. There are a lot of museums that are in factories, or an old warehouse, an old warehouse or a historic house, or there's a lot of former lives to the buildings that museums now inhabit. And I'm wondering how that, or if that, um, factors into the decision making of the kinds of systems.
Yeah, I mean, so if I take it first up this, Rob.
Yeah, go ahead.
I think actually for the historic buildings, actually, geothermal is a really compelling option because it has less of a physical footprint. So much of the equipment is buried under the ground that,
Mm.
if you want to preserve that historic aesthetic for a lot of these historic
The
buildings, again,
duct and the ductless options, yes.
yeah, absolutely. But um, Yeah. Anyways, so I think like that's one component where we're talking to a number of historical church, excuse me, museums and other institutions where again like that's a really key part where they're not allowed to have the air handlers out visibly outside for an air
Hmm.
source system, but the geothermal system is actually compatible with the historic preservation restrictions and or
Hmm.
just the institution's own goals of preserving that feeling of being historic. But Rob, yeah, please.
And I'll just add, so, to take more, I think Craig covered sort of what the benefits on the exterior and sort of the aesthetics, and like, would it be okay to be looking at 7 foot tall VRF, units on a roof or outside or something like that versus say being able to bury it in a basement. But I think the bigger impact is on the internal loads, and what are, if you're going to be converting to something that is most efficient at 110 to 130 degree temperatures, how does that impact your interactions with the envelope? And do you need to add supplemental heat at some of your perimeter zones that might not start to feel drafty in an old warehouse or in an
Hmm.
old factory building? How cavernous is the opening that you're going to be in if you were depending on pure convective heat? Do you now need to consider, in the Wells Village Church inside their sanctuary, we actually added small booster fans on their historic, old steam radiators so that we could actually make sure that we're pushing that instead of that convective heat we would have expected at 180 degrees, now we had a chance of potentially stratifying some of that heating. And so it just takes a more thoughtful approach to the inside, if we're dealing with some of those historic or cavernous type environments.
I had a couple questions. I'm with Rough Point in Newport, Rhode Island. I'm the maintenance technician there. I'm filling in for Amy, our chief finance officer, who set this up. But we just finished going through, or we're in the process of going through a renovation, adding a wing of our building with VRF units. So I think this would maybe fit more with when we do eventually replace our boilers or our chiller and tower system for our AC. But one of my questions that I think would be helpful for everyone was, what's the diameter of these bored holes? And then a question that would be specific to us is this something that is feasible on an oceanfront property?
So the boreholes generally are going to be about 6 inches wide. They can vary. Some bores are as narrow as 4 or 5 inches. But I would say in general, we've got a 6 inch casing. You're going to have 2.5 inch pipes that will go down, that they come pre-sealed as a U-bend. They go down, they are set to the length of the bore. Those get dropped into the hole, and then so the steel casing runs from the surface all the way down to the competent bedrock. They push that casing into the rock, and then from there to the bottom of the hole, it's just bedrock. And so then you fill that borehole up with conductive grout, which helps with the heat transfer from the piping out to the rock. But each bore generally about 6 inches. And then your second question was oceanfront property. So yes, it's feasible. Sometimes some of the challenges that we face on oceanfront properties is a more casing that's required before you get to the competent bedrock. You might be dealing with really sandy conditions, sandy soils down to the competent bedrock. A recent test well we did was going to require about 200 feet of casing versus say another one where a bedrock's closer to the surface, it might only be 40 or 60 feet. You may also be dealing with more groundwater, and so that may limit the amount, the depth that it's really feasible to drill down to before the water management, the amount of water pushing back at you as you're trying to drill down just becomes infeasible. And then I guess maybe the third question that's worth considering is, actually using the ocean water as a potential heat exchange. And those are feasible, but, come with their own challenges around permitting and managing, that water source. But those types of, water source exchange do exist and are considered by design teams.
I think that just add is you might not want to replace metal casing with plastic casing in terms of worrying about saltwater corrosion as you're designing the piping there. You won't want a potential difference, but
Sure. Awesome. Thank you. I'm sure if we decide to move forward, I'll have many more questions, but one last question that I have today would be for anyone, if they were to do a test drill hole to determine how many holes you would need and how deep the hole would be. Is that paid for only if the project moves forward, or how does that work for test holes in the preliminary stages?
So typically, an initial feasibility study would not include a test bore. If the initial economics made sense to explore further, then we would, a test bore would be included and usually, paid for as part of a design study. So, underneath that, underneath the engineer, essentially, the engineer would hire a driller to do that test bore and then use that to inform a more complete, DD, 60% DD type design at that point.
but generally,
no, it's just, is that cost sort of tied to how deep you have to go? I mean, can you give us a ballpark of what that would cost for the test? Do you know? I don't know if there's.
Generally, I mean, you're talking about mid 5 figures, so somewhere between $40,000 and $60,000. But again, some of our drillers will say, I don't know what kind of water management I'm going to say, so here's my base drilling cost and here's my allowance in case I end up having to deal with a lot of water here.
But I say you usually don't really get to that stage unless this is a very serious option. It's pretty likely to move forward, as a geothermal system, and then almost always that test hole we want to use as one of the actual boreholes for the system. So it's not like wasted labor. It's just really the first hole that you use for the system.
Right.
Yeah. Sure. Thank you.
We are just about at the top of the hour, so I want to respect everybody's time. Thank you so much to Rob and Craig. I think this was really informative. Is there a way to be in touch with y'all if folks do have some follow-up questions or something that's percolating that we didn't get to today?
Yeah, you can email either Craig and I, and maybe we can share our contact information. Maybe you can send us out with the recording at the end of the.
Great.
Yeah, it looks like Craig's just dropped his email and Rob's email into the chat here. And yes, happy to do that as well. So thank you again. Thanks so much. Thanks everybody for joining.
That was great.
And we'll see you next time.
Yeah.
Yeah. Thanks so much, everyone.
Thanks,
Thank you.
everybody.